First, we cast a ray through each of the pixels in the image plane. We then traverse each ray. All of these traversals are done in parallel. When we find an isosurface intersection, we mark it in our prediction buffer. Note that we call this type of traversal full traversal. Let's assume the user rotates the viewpoint by some small angle d theta. Here, we see that this ray didn't intersect the isosurface on our previous render. Therefore, we simply traverse the ray by stepping along it by some fixed amount dt. Since this requires no branching, it is well suited to GPU execution. We call this sparse traversal. Here, we traverse this ray in a back and forth manner, again using dt as our step size. We call this local traversal. We traverse the next 4 rays using local traversal. We are likely to find the isosurface at a depth near our prediction value. This coherence greatly speeds up rendering. Here we see another case of sparse traversal. However, this time we find another isosurface intersection and mark it in the prediction buffer. Recall that we stepped along the ray by a specified interval dt. We need to choose dt such that we get an acceptable trade-off between image quality and speed. We will base our formula for dt off the dimensions of an individual voxel. We can't use just one width, like dh, because voxels are not necessarily cubic. Our formula for dt takes one parameter, kappa. Here we see how kappa affects rendering time, assuming all pixels are rendered with sparse traversal.